Hello. Today we're going to talk about the mean value theorem. First, let's review some concepts of differentiability. Say that I is a closed interval from a to b and f is a well-defined function on this closed interval. Given a point P in the interior of I, that is, P is between A and B but not equal to A and B, we'll say that a function f is differentiable at P if the following limit exists. The limit as x tends to P of f of x minus f of P divided by x minus P. In this case, we'll denote f prime of P as the limit, and we'll call this value the derivative of f at P. We've seen that differentiability implies continuity. That is, if f is differentiable at P, then f is continuous at P. We also found a few formulas if we're given two differentiable functions f and g. First, their sum is differentiable, where the derivative of f plus g is f prime plus g prime. Similarly, their product is differentiable. That is, the derivative of f times g is equal to f times g prime plus f prime times g. Using this, we can see by induction that polynomials are all differentiable. And finally, we have the result that we call the chain rule. Let's say that f is a function from I to r, and g is a function from j to r. We'll assume that the image f of I is contained in j so that the composition g circle f makes sense and is well defined. If f is differentiable at p, and g is differentiable at L, which equals f of p, then the composition is also differentiable at p. In particular, the derivative of g circle f is equal to g prime evaluated at L times f prime evaluated at p. Today we're going to talk about the mean value theorem and how we can express it in several ways. Let's begin with what we'll call the interior extremum theorem. Let's let I be an open interval and say that f is differentiable in our open interval I. Assume first that f attains a maximum at some p in I. That is, f of x is less than f of p for all x in I. Then f prime at p equals 0. Similarly, assume that f attains its minimum value at some p in I. That is, f of x is greater than or equal to f of p for all x in I. Then f prime of p also equals 0. First, let's assume that f attains its maximum value at some point p. Since I is an open interval, then we can find a sequence of numbers a sub n and b sub n that get closer and closer to p. Intuitively, we want to say that a gets closer to p coming from the left, and b sub n gets closer to p coming from the right. Since f of x is less than or equal to f of p, let's define two new sequences c sub n and d sub n. C sub n is the ratio f of an minus f of p divided by an minus p. Since f of an is less than or equal to f of p, the numerator here is less than or equal to 0. The denominator is also less than or equal to 0 because a sub n is less than p. This means that the ratio c sub n should be greater than or equal to 0. Similarly, let's define d sub n as f of bn minus f of p divided by bn minus p. Again, the numerator is less than or equal to 0, but the denominator is greater than or equal to 0 because b sub n is greater than p. This means that d sub n is less than or equal to 0. But now, a sub n and b sub n both tend to the point p. So using the sequential criterion for limits, we see that f prime of p must be equal to the limit of the c sub n's as well as the limit of the d sub n's. However, since the c sub n's are greater than or equal to 0, we see that f prime of p, their limit, must also be greater than or equal to 0. Similarly, the d sub n's are less than or equal to 0, so f prime of p, their limit, must be less than or equal to 0. But putting both of these together, we do indeed see that f prime of p must be 0. Now let's assume that f attains its minimum value at some point p. We can now define a new function, g of x, which is just negative f of x, and we see that this attains its maximum value at p. So by using the previous part, we see that f prime of p equals negative g prime of p equals 0. As a corollary, we'd like to prove what's called Darboux theorem. Let's let I be a closed interval from a to b and say that f is differentiable on this closed interval I. Let's assume that there exists an L between f prime of a and f prime of b. Then there exists a point P in our closed interval, since that actually P is in the interior, that is, P does not equal to a or b, and f prime of P equals L. This result is named after the French mathematician Jean-Gaston Darboux. And notice that this result states that the derivative has the intermediate value property. Let's discuss the proof. Let's consider a new function g on our closed interval I that's defined by g of x equals f of x minus L times x. Then we see that g is differentiable on I, and in fact g prime of a, which equals f prime of a minus L, must be negative, whereas g prime of b, which equals f prime of b minus L, must be positive. It suffices then to show that there exists a point P in the interior so that g prime of P equals 0. First, I claim that there exists a point C in the interior such that g of A is greater than g of C. Assume to the contrary, that is, that g of A is less than or equal to g of C whenever A is less than C is less than B. Then we can consider the ratio g of C minus g of A divided by C minus A. Because g of c is greater than or equal to g of a, we see that the numerator is positive. And because c is greater than a, we see that the denominator is positive. Therefore, the ratio is greater than or equal to 0, which means that the limit as c approaches a must be g prime of a must be greater than or equal to 0. However, this contradicts the assumption that g prime of a is less than 0. So, such a c must exist. In a similar way, there must exist a d such that g of b is greater than g of d. Putting both of these together, we see that g of a and g of b cannot be the minimum of our function. So there must be another point P where we have a minimum. To be more precise, we know that g is differentiable, therefore it's continuous. Also, our closed interval I is compact, so g must attain its minimum at some point P. As we just said, this minimum cannot occur at either A or B, so our P must be in the interior of this closed interval. Now we use the interior extremum theorem to see that our P satisfies f prime of P equals 0. We state another result, known as Rolle's theorem. Again, say that I is a closed interval, and let's denote I0 as the open interval from A to B. This will be its interior. Let's say that f is continuous on the closed interval I, yet differentiable on the open interval I circle. If f of a equals f of b, then there exists a point P in the interior so that f prime of p equals 0. This result is named after the French mathematician Michel Rolle. Since I is a compact set, we know that f attains its minimum value at some point f of d and attains its minimum value at some point f of c. That is, f of c is less than or equal to f of x is less than or equal to f of d for all x in our closed interval I. Let's consider now three cases. First, say if we can choose our minimum value to occur at a point c that is different from a or b. This means that f of c is less than f of x for all x in I. However, this now means that f attains its minimum value at some point p in the interior. Now let's say that we could choose a maximum value to occur at some point d also not equal to a or b. This means that f of d is greater than or equal to f of x for all x in I, so that f attains its maximum value at some point p in the interior. Finally, we really have four cases to consider, either c and d equal a, c and d equal b, c equals a and d equals b, or c equals b and d equals a. In either of these cases, we see that f of a equals f of x equals f of b, so that f must be a constant on our closed interval. In particular, the derivative f prime must be 0 for any point p in the interior. So in either case, we see that there does exist a point in the interior so that f prime of p equals 0. As a corollary, we have the theorem of today, which is the mean value theorem. Let's say that I is a closed interval and I circle is its interior as before. We'll say that f is continuous on I, yet differentiable on its interior I circle. First, there exists a point in the interior such that f prime of p equals the ratio f of b minus f of a over b minus a. Second, f prime of p equals 0 for all points p in the interior if and only if f is a constant on the interior. Let's show the first statement. We'll consider a new function g defined as follows. We take the ratio f of b minus f of a over b minus a, multiply by x minus a, add f of a, and subtract f of x. We've defined this such that g is a differentiable function where its derivative, g prime of x, is equal to the ratio f of b minus f of a over b minus a minus f prime of x. We've also set up this function such that g of a equals g of b equals 0. So Rolle's theorem asserts that there is some point p in the interior where g prime of p equals 0. But this is exactly the statement that f prime of p equals f of b minus f of a over b minus a. Let's show the second statement. First, assume that f is constant. Then on any sufficiently small region that where x does not equal to p, we see that the ratio f of p minus f of x minus f of p divided by x minus p must be 0. So if we take the limit as x tends to p, f prime of p must also be 0. Conversely, assume now that the derivative is 0. Then for any distinct x1 and x2 in the interior, we can find a point p such that f of x1 minus f of x2 divided by x1 minus x2 equals f prime of p. However, this must be 0 because we're assuming that our derivative is 0. So this means that f of x1 equals f of x2 for any pair x1, x2 in the interior. But this is exactly what it means to say that f is constant on the interior. We can also state the mean value theorem in a slightly more generalized form. As before, say that I is a closed interval, I circle is its interior. Now say that we have two functions f and g that are continuous on I, yet differentiable on the interior. Then there exists a point p in the interior such that f of b minus f of a times g prime at p equals g of b minus g of a times f prime at p. To see why, let's consider a new function h defined on the open interval as follows. H of x equals f of b minus f of a times g of x minus g of b minus g of a times f of x. This is a differentiable function on the interval I such that h of a equals h of b. But now Rolle's theorem asserts that there is a point p in the interior such that h prime of p equals 0. But this gives exactly what we wanted for the generalized mean value theorem. Thanks very much for watching.